All right, lesson 3, similarity. Here we're going to be proving that triangles are similar. No, we just have a couple, about 3 theorems that we're going to apply to basically say, hey, these triangles have to be similar, without going through the whole process of saying, hey, we've performed this dilation and therefore they're similar, or hey, I've confirmed that all of the corresponding sides are proportional and all the corresponding angles are congruent. We just have some shortcuts. So we are going to use a little bit of that rigid motion dilation understanding that we hopefully not perfected, but got better with over lessons 1 and 2, to use kind of our train of thought or line of thinking to prove that we are dealing with similar triangles. Now, the hope for that, if we understand that we are working with similar triangles, then we can apply those proportions to do indirect measurement, etc. There's lots of different applications we can go from here. So just like we have triangle congruence shortcuts, like side, 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 angle, side, etc., we have triangle similarity shortcuts. So we're used to using these theorems, these shortcuts back in Unit 4 when we were proving that our triangles were congruent. That was only for triangles. It didn't work with quadrilaterals or pentagons or whatever else, but it worked with triangles. Likewise, today I've got a couple of shortcuts that we are going to be using for similarity. Angle-angle similarity, side-side-side similarity, and side-angle-side similarity shortcuts. So very similar in structure to the way that we wrote down those theorems before. The only difference is that we have this little tilde at the end, which you should recall at this point means similar, or similarity, or is proportional to. And so we're going to be using that little tilde there to say that we are dealing with similar or similarity shortcuts here. All right, so the first is angle-angle similarity. And the reason why this works is because when we have 2 pairs of angles congruent, we know by the third angles theorem back in lesson 1 or 2 of Unit 4, we know that the third pair of angles will also be congruent. What we can also do is juxtapose these figures, organize them and arrange them in such a way that we can prove and we can model that what we're dealing with is a dilation and either a translation or reflection or whatever. So if 2 angles of one triangle are congruent to 2 angles in another, then those triangles are similar. And if they are similar, that means that all of their corresponding sides are proportional, all of the corresponding angles are congruent. All right? And so we can use reflect this and then rotate that and translate that so that it lines up over this other figure to show that we are dealing with a dilation. The side-side-side similarity shortcut does basically the same thing. If the corresponding sides, all the corresponding sides of 2 triangles are proportional, then those triangles are similar. Now this gets a little bit tricky because we have to make sure that we organize the proportions in the correct way. If I switch and I pair up the wrong pair of sides, then this no longer works, right? If I say AB over DE is equal to AC over EF, it may not actually be equal there, but we still may have similar triangles and proportional sides, so we have to be attentive for which sides go where. I'll give you some strategies on that here in just a little bit, so that when we write our proportions, we can confirm that we are dealing with the same K value, right? The same scale factor. And then our final similarity shortcut is the side-angle-side similarity shortcut. And just like side-angle-side in Unit 4, we're talking about 2 pairs of sides and the included angle, all right? So we've got this pair of sides, and then the angle that is included between those pairs of sides. So we want to make sure that we're dealing with the right pairs, that we structure our proportions correctly, and that we have, obviously, that pair of congruent angles. So all that these shortcuts do for us is it allows us to, of course, show that we're dealing with similar polygons, similar triangles, without having to have all of the information given. All right, we don't have to say, I have 3 pairs of proportional sides, I have 3 pairs of congruent angles. Instead, I can be limited with a little bit of information, and now I know that those other things are true about those figures being similar. All right? And so here's a couple items that we're going to look at here. Is triangle ABC similar to triangle DEF? So this is what's called a similarity statement. Similarity statement. We've been using that a little bit here and there. A similarity statement And this says that A goes to D, B goes to E, C goes to F. All right, so segment AB and segment DE are supposed to be proportional. And we're supposed to have segment BC and segment EF. And we're supposed to have, and actually we don't know if these are equal yet. We're going to find out if they're equal. And we have C back to A is F back to D. We want to confirm that these ratios are in fact equal to each other. So we're kind of asking the question, are these equal to each other? All right, and so we're going to take the length for AB, the length for DE. We're going to take the length of BC and the length of EF, the length of AC and the length of DF. And we're going to check in our calculators to make sure that these are all equal to the same amount. And it turns out that using our calculators, we are going to find out that these are all equal to 2/3. If they are all equal to the same amount, that is our K value. And these triangles are now, we can confirm, are similar because all three pairs of corresponding sides are proportional, all right? All of these ratios are equal to each other, therefore this is a proportion, and they're all equal to our scale factor, all right, 2/3, all right? Wonderful, wonderful, wonderful. Are these triangles similar? So this one's a little bit different, and I'm not gonna have you do this one because I wanna highlight a key trick here. Here I was given a similarity statement to test. Is this side corresponding to that side? I'm sorry, is this side proportional to that side? Is this one proportional to that? And then is the third pair of sides, are they proportional? So I knew which ones to line up. Obviously here I can kind of tell, you know, where the hypotenuse is, if this is a right triangle, and then I've got the two legs that are kind of, are they interchangeable or do I know which one goes where? Over here it's a little bit fuzzy because if I'm looking at this, I'm gonna say, does 20 over 12 equal 16 over 15 equal 24 over 18? Right? Just by looking at the picture, I would say these go together, and those go together. All right? And so is triangle ABC similar to triangle DEF? Well, if this were the case, the answer would be no, because these fractions are not equal to each other. And you can tell pretty quickly that this is just a little bit bigger than one, and this is quite a bit bigger than one. All right? So you don't even have to use your calculator to know that these are not equal to each other. All right? So here we know that triangle ABC is not similar to triangle DEF. I'm going to cross that off, are not similar to triangle DEF. All right, however, look at the order of the sides. 12, 15, 18. They get bigger. They go from the smallest side to the longest side. This one goes 20 down to 16 and then back up to 24. So the way that these triangles are organized or are oriented, it's like this one is flipped. If I redraw FED, so I have 16, 20, and 18, I'm sorry, and 24, my bad. Now, let's check. Let's check to see if 16 over 12 is equal to 20 over 15, if that's equal to 24 over 18. And it turns out that in fact these are all equal to 3/4. All right, these are all equal, I'm sorry, not 3/4, 4/3. These are all equal to 4/3. All right, these are all equal to 4/3. Therefore, this triangle is similar to that one. These triangles are similar, but not in the order in which we wrote our similarity statement, all right? So the actual similarity statement there is that triangle ABC is similar to triangle FED. This was a little bit tricky, so I wanted to make sure that I got to show you that in a video example so that you could rewatch that as needed. All right, lots of information going on there. Obviously, rewatch that part if you need more information. Moving on here. Are these two triangles similar to each other? We don't have a ton of information. This isn't spraying very well. Let's figure out what's going on. I got these pictures right here. And we want to know if these are if these two triangles are similar. And so what we don't have is 3 pairs of sides, so I can't use side similarity like I did in the last example. I don't have 2 pairs of angles similar because none of my angles are marked, all right, so that's kind of problematic. Do I have side angle side? Well, I've got 2 pairs of sides that I can check to see if they're proportional, but then where is the included angle? And so what I want for us to recognize is that in this picture, I've got this segment is 18, PQ. I've got this whole side, QS, is 27. It's 15 plus 12. And in between those sides is this angle Q. It's a shared angle. So angle Q is congruent to angle Q. It's reflexively congruent to itself. And then on this other triangle, it's like I moved it down and I rotated it as well, all right? So 12 is going from R to Q, and 18 is going from Q to P. So what I want to check is 18 over 12 equal to 27 over 18? Are those equal to each other, yes or no? And so we can confirm in our calculators that this is 6 times 3 over 6 times 2. This is 9 times 3 over 9 times 2. So these are both equal to 3 over 2 as our K value. You can confirm that in your calculator. And therefore, these sides are proportional. These included angles are congruent to each other. Therefore, yes, these triangles are congruent by the side angle side similarity. All right, we can show that we've got that that information. A pair of proportional sides, or two pairs of proportional sides, and the angle that's included between them is congruent. All right, good stuff so far. Good stuff so far. All right, last little example. Did he say last example already? Oh my goodness. You know, we're only 12 minutes into this. How's this go? Take a look at this image. And I don't know how well you can see this on the screen, but basically what we have is Avery is out here playing in the yard, and she's looking at an antenna tower in the yard that casts a shadow that is 40 feet long. Avery is 6 feet tall, and Avery's shadow is 5 feet long. And so the question is, and this is obviously not drawn to scale because this looks shorter than the actual 5-foot shadow, but whatever. And so the question is, how can we determine the height of the antenna? How can we find the height of the antenna? Well, what we're going to notice, what we're going to trust and believe is that the angle of the sun creating the shadow means that this angle is going to be the same for both the person's shadow and the antenna's shadow. All right, that line. All right, it's going to give us the same angle with the ground. And then both of the person and the tower are hopefully standing straight up, and so they're perpendicular to the ground. Therefore, these triangles are similar by angle similarity. Okay, so the triangles are similar. Now we get to use and apply our proportions to say, I know that these triangles are similar. I know that their sides, therefore, are proportional. It lets me create an equation that now I get to solve. So the length of the shadow, of Avery's shadow, to the length of the antenna shadow is going to equal the height of Avery over the height of the antenna. Now here's the fun thing. It doesn't matter exactly how you make this. It just matters that you have the corresponding parts lined up. All right? I could have said, I want to compare 40 to 5, and that's going to equal x over 6. And what we want to do is we always want to compare something from one figure to something in the other. We could compare within the figure. I feel like it just gets a little bit messy and might confuse us moving forward. So we could write that either way, and it will still work out. Because when we do our Algebra 1 cross-product property here, we are going to be able to solve this equation. All right, so 5 times x is doable. 6 times 4 is 24, so 6 times 40 is 240. When I divide that by 5 on both sides, I get 48. So that means that the tower, the antenna tower, is 48 feet tall. All right, I solve for the variable. I'm able to answer the question, all right, with units. Whenever we do word problems, real world problems, we want to make sure that we use units and answer with complete sentences as much as possible. All right, good job. We just did some indirect measurement. You are hopefully able to apply your thinking about rigid motions and dilations and prove that triangles are similar using angle similarity, side similarity, or side angle side similarity.